Okay, in 10.1 we were comparing two proportions. Now we're going to be comparing two means. What is meant by the sampling distribution of the difference between two means? It describes the possible values of x bar sub 1 minus x bar sub 2 and how often they will occur. We can take the distribution of x bar for one population, or one sample, and the distribution of x bar for another, subtract the two, and get a new set of distributions. What are the shapes that are in spread of the sampling distributions for x bar and x minus x bar 2, and are there any conditions that need to be met? Both x bar 1 and x bar 2 are random variables. The statistic x bar minus x bar 2 is the difference of these two random variables. In an earlier chapter, we learned how to combine data, and we found the mean of two different samples to be the difference of those two samples, and we found that the variance of the difference was equal to the variance of each added together. So when we apply this to what we're working on now, we are going to see that the shape, when the population distributions are normal, the sampling distribution of the difference of the means is approximately normal as well. This will be the case as long as the sample sizes are large enough, and we need to make sure that both samples are greater than or equal to 30. The mean of the sampling distribution is just the difference of the samples, and the standard deviation of the sampling distribution of the mean of the difference of two means is the square root of the variance divided by the population, or by the sample size added together. So we have the square root of the variances divided by the sample size added to each of them. This works as long as there is no more than 10% of the population included in the sample. So what is the standard error of the difference of two means? Well, when the 10% condition is met, the standard deviation is the following equation. However, since we do not know the values of the parameters for sigma 1 and sigma 2, we replace them in the standard deviation formula with the sampled standard deviations. The result is the standard error of the statistic given by this equation. This measures how far the difference in sample means will typically be from the difference in population means if we repeat the random sampling or random assignment many times. You will need to know these formulas. They are not on the formula sheet. What is the formula for a two-sample t-statistic? Again, the generic version of this formula is on the formula sheet, but you will need to remember or memorize it. It measures how far the difference in the sample means is from 0 in standardized units. What are the conditions for performing inference about the difference of two means? Well, same as all of our conditions that we've been working on lately. They need to be random. The 10% condition needs to be met, and there needs to be normal or large samples. So in order to meet this one, we need our sample sizes to be greater than or equal to 30 for both populations. And if either population has an unknown shape or the corresponding sample size is less than 30, we need to use a graph of the sample data to assess the normality of the population distribution. We cannot use two-sample t procedures if the graph shows a skewness or outliers. What distribution does the two-sample t-statistic have? And why do we have a t-statistic rather than a z-statistic? And how do you calculate the degrees of freedom? The two-sample t-statistic has approximately a t-distribution. We can use technology to determine degrees of freedom, or we can use a conservative approach using the smaller of n1 minus 1 and n2 minus 1 for the degrees of freedom. The calculator is going to compute it using this formula, but if you're not using the calculator, I highly recommend you just take your sample size and subtract 1 and determine which one is less. We use t rather than z when we do not know the population standard deviation. So this is the same as what we covered in chapter 9. Let's look at an example. After buying many helium balloons only to see them deflate within a couple of days, Aaron and Jenna decided to test if helium-filled balloons deflate faster than air-filled balloons. To find out, they bought 60 balloons of the same type and randomly divided them into 2 piles of 30, filling the balloons in the first pile with helium and the balloons in the second pile with air. Then they measured the circumference of each balloon immediately after being filled, and again 3 days later. The average decrease in circumference of the helium-filled balloons was 26.5 centimeters, with a standard deviation of 1.92. The average decrease of the air-filled balloons was 2.1 centimeters, with a standard deviation of 2.79. Why was it important that they use the same types of balloons? And what is this called in an experiment? Well, this is called control. Using the same type of balloon eliminates a possible source of variability, making the standard deviation smaller and increasing the power. Does this data provide convincing evidence that helium-filled balloons deflate faster than air-filled balloons? Well, we need to run a test in order to figure that out. We're going to state, plan, do, and conclude. So we want to perform a test with a null hypothesis that the mean of the heliums minus the mean of the air is equal to 0, or that there was no change, versus the alternative hypothesis that the mean of the helium minus the mean of the air is greater than 0, showing that the average deflation of the helium-filled balloons was greater than the air-filled balloons. We are going to do this with a significance level of 5% because they didn't tell us otherwise, or an alpha level of 0.05, where the mu sub h represents the mean decrease in circumference of helium-filled balloons after 3 days, and this should say mu sub a is the mean decrease in circumference of air-filled balloons after 3 days. We're going to plan on running a 2-sample t-test for the difference in means of the helium and the air-filled balloons if all the conditions are met. Random, the data came from 2 groups in a randomized experiment. 10% condition is not necessary because there was no sampling without replacement. You would need to write that down. We don't need to check for 10% because there was no sampling without replacement. And normal/large sample, we need our sample sizes to be greater than or equal to 30. In this case, they are both equal to 30. So we can move on to our do. We plug everything we know into our t equation. We get 39.46. And then we can run a t-CDF to identify that our p-value is approximately equal to 0. I recommend you taking a moment and plugging these values in and trying to make sure that you can get these answers as well. Of course, you can also run the whole thing in your calculator by finding the 2-sample t-test, plugging in all the information that you know about each individual population, identifying that we want mu1 to be greater than mu2, and that the data is not pooled. That is a big one. Make sure that you say no on pooled. The calculator then gives you that t is equal to 39.46, our p is equal to 0, and our degrees of freedom are 51.4. We can then conclude that because the p-value is approximately 0 is less than our alpha, we reject the null. There is convincing evidence that helium-filled balloons deflate faster than air-filled balloons. In context to our problem, we would say there is approximately a 0 probability of getting a difference of 24.4 centimeters or more by chance alone, assuming that the mean decrease in circumference is the same for helium-filled and air-filled balloons. So what they did is they take our p-value of 0, which is the probability of getting what we were looking at. We were looking at the difference in the means Well, 26.5 minus 1.92 gives us about 24.4. And then we have to relate it back to the problem, which is our null hypothesis, assuming that the mean decrease in circumference is the same for helium-filled and air-filled balloons. I'm going to stop there, and I'm going to make a separate video for the second part of this unit.